Welcome to the presentation of the paper Radio Localization Sensing Part 1 Fundamentals. My name is Wymeersch and I'm with Chalmers University of Technology. This work was performed in collaboration with Gonzalo Seco-Granados from UAB in Barcelona, Spain. This presentation summarizes the paper in IEEE Communications Letters Radio Localization Sensing Part 1 Fundamentals. There's an accompanying video for the second part of this paper, which you can also find on YouTube. This is the outline of this presentation. I will first introduce the main concepts of positioning, localization, and sensing, followed by the relevant problem definitions, as well as the associated models. Then I will define the most important performance metrics, and then show how localization sensing methods work. I will wrap up with some conclusions. So let's first start with some terminology. The term positioning refers to determining the location of a connected device, like a smartphone, in a global coordinate system. In a modern context, positioning can also include estimating the orientation of the device in 3D. The term localization can refer to the same as positioning, so estimating the location or orientation of a connected device, but it can also refer to estimating the location of a passive object in a local or a global coordinate system. Sensing is a much broader term, which includes radar sensing. For radar sensing, sensing means detecting of passive objects and estimating their state, where the state typically includes the position and velocity in a global or a local coordinate system. As an example of a local coordinate system, you can for instance think of a car radar. A car radar detects objects in front of the radar in the local frame of reference of the car. If the sensor is a base station, then the base station would sense the object in a global coordinate frame, especially when it involves multiple base stations. And finally, SLAM, which stands for Simultaneous Localization Mapping, involves the two components. So first of all, sensing of passive objects and determining their locations, while localizing a connected device. And there, we use locations of the passive objects to improve localization, and vice versa. The figures in the bottom show these different terms. The first figure refers to localization or positioning of a connected device, where we localize, for instance, a smartphone from angle of departure measurements from different base stations, or from time difference of arrival measurements. The localization is done in a global frame of reference agreed upon by all the base stations. The figure in the middle shows monostatic sensing, here initiated by a user device. So the user device emits a waveform, which is sent over the air and scatters back from the different objects, in this case a car and a building, and reaches back to the smartphone. So the smartphone would operate both as transmitter and receiver, and would then localize the object in its local frame of reference. The figure on the right shows an example of bistatic sensing, where the transmitter and the receiver are separated, so the transmitter could be a base station, the receiver could be a smartphone. The base station in this case sends a signal downlink to the phone. The signal goes in a line of sight path as well as paths scattered of different objects. And in this case, the smartphone would aim to localize itself and also map the objects in the environment. Let's now move on to more specific channel models and problem definitions. This is the channel model that we will use, which corresponds to a channel matrix H indexed by a subcarrier N and a symbol K. So this means that for each frequency or subcarrier N and each time instant K, we have a matrix. This matrix is a superposition of a number of paths. This is also shown in the figure where there's a transmitter and a receiver, and in this case two multipath components. Each of the paths has a complex channel gain, so it has an amplitude and a phase. With each path there's also an angle of arrival, which can be computed in azimuth and elevation, which is an argument to the steering vector of the receiver, in this case the user side. So the user has a steering vector if it has an array and has as argument the angle of arrival in azimuth and elevation. At the transmitter side, the base station side in this case, there's also a steering vector, which takes as arguments the angles of departure, again in azimuth and elevation. All of these angles are indexed by the path, L. Next, there's the impact of the frequency, or subcarrier index N, which leads to a linear phase progression, which depends on N, the subcarrier spacing, delta F, and the path delay, tau L. And finally, there's a linear phase progression across time, depending on the time index K, the symbol duration Ts, and the Doppler nu L. In most cases, there are many propagation paths. These paths can include the line of sight path, so the direct path from the transmitter to the receiver, as well as non-line of sight paths that go via the environment. These could be single bounds, as shown in the figure, but also multi-bounds. At lower frequencies, so below 6 GHz, there's a complex relation between the channel and the underlying geometry, because of all the physical propagation effects. At millimeter wave ranges and above, there's a more pronounced geometric relation between the channel and the location of the user, the base station, and the objects. This makes the channel sparser and more easy to interpret. For that reason, localization sensing at millimeter waves and higher is of special interest. Now we add our signal model. We again look at a subcarrier N and a symbol K. This observation at the receiver is now a vector indexed with N and K. The observation depends on the channel, H and K. It also depends on the combiner used at the receiver, here W, which goes from the antenna element dimension to a lower dimension. And it also depends on the precoder that is used, here denoted F and K. So at each symbol K, at each time instant, a single precoder is used, denoted by F and K, and this precoder includes both the spatial precoding as well as any pilot symbols or data symbols. And then there is the noise. For most positioning and sensing applications, the precoder is known. Either it contains pilots or known data and must be energy constrained. The noise is typically modeled as complex Gaussian noise with variance N naught. So now, from these observations, we want to estimate the geometric channel parameters of the line of sight path and then turn those into a position estimate. First, we will talk about the localization problem. The localization problem is visualized on the right. There are, in this case, 3 base stations sending and downlink signals to the user. These signals are sent at the same time but on orthogonal subcarriers. Between each base station and the user, there's a corresponding channel, indexed by the base station index, H1, H2, H3. The channel depends on the subcarrier index N and the time K. The channel depends on geometric parameters, including the delay of the different paths, the angles of the departure at the base station, and the angles of arrival at the user. The user thus observes the signals from all of the N base stations in downlink. From these observations, it must estimate the parameters of the line of sight paths, the angles and the delay, and remove or extract only the line of sight information, because the multipath information is a pure disturbance here. Once we've estimated the angles and delay of all of the line of sight paths for all of the base stations, we can then localize the user. The channel from base station I is denoted H, I, and K, again, depending on the base station index I, subcarrier index N, time index K. It comprises a line of sight part, so this is a rank 1 line of sight channel, and all of the non-line of sight components. These act as a pure disturbance. The line of sight channel, again, is rank 1, has a complex channel gain. It has the receiver side steering vector, depending on the line of sight angle of arrival in azimuth and elevation. The transpose of the base station steering vector, depending on the angle of departure in azimuth and elevation. And then the phase rotations due to the delay, and due to the Doppler as a function of subcarrier index and time index. We now relate the geometric information to those angles and delays. In particular, the geometric information we can extract from the signal from base station I, we denote by eta I, contains the angles of arrival, angles of departure, delay, and Doppler. And all of those parameters together, they depend on the user position and also the user orientation. In particular, the angles of arrival depend on the user orientation and position, while the angles of departure only depend on the user position, but not the orientation. Let's give some examples of how the geometric parameters of angles and delay relate to the user state. The most easy case is the time of arrival. So the time of arrival of the line of sight path from the ith base station depends on the user position through this expression. It is the distance between the ith base station and the user position over the speed of light plus the clock bias of the user. There is a clock bias because the user is typically not synchronized to the base station to the extent needed for positioning. The angle of arrival, theta, can be written as an expression of the user position and the user orientation. The expression is somewhat involved because it depends on the local coordinate system and the orientations involved, so I don't write it explicitly. The angle of departure only depends on the user position. You can see this by the fact that the angle of departure determines a line from the base station towards the user. If the user is in the same position but has a different orientation, the angle of departure does not change. Finally, there's the Doppler. Even though in principle the Doppler provides geometric information, this information is often not considered for two reasons. First of all, there's the carrier frequency offset of the user, which must be compensated for and which mixes with the Doppler. And secondly, for short transmissions, as is common in 5G and 6G systems, there's not much Doppler information in the observation. For that reason, we will absorb the Doppler into the complex channel gain, since the phase does not change much during a typical transmission duration. Finally, there's the channel gain. If we look at the power of the channel gain, it is given by this expression. This is pure free space path loss, which depends on the wavelength lambda, the gain at the receiver, the gain at the transmitter, depending on the angle of arrival and angle of departure, and the distance squared. The phase of the complex channel gain is typically modeled as a random, unknown, and uniform phase. We see that even though the amplitude depends on the distance, the dependence is quite complicated because of the angles that appear here in these gains. For that reason, the channel gain is typically not used for positioning, and only the information provided by the time of arrival, angle of arrival, and angle of departure is used as providing significant position information. Now let's define in more detail the sensing problem. We will consider a monostatic sensing scenario where the transmitter and the receiver are co-located. In this case, the base station is a monostatic sensing unit which sends a signal towards the environment. The signal scatters back towards the base station. So there's no communication happening in this case between the base station and the car, only the backscattered signal is processed. The channel observed by the base station has two components. There is a part related to the objects and a part related to clutter. The objects are typically the moving entities in the environment, and the clutter is typically background noise or ground reflections and so forth. Now, the part of the channel related to objects is again, as in the previous form, which depends on angles of arrival, angle of departure, delays, and Dopplers. So, while in the positioning case, you're only interested in the line of sight path, here we actually care about all the multipath components. So each of the paths L, we want to extract their geometric information. Let's see how this geometric information relates to the state of the objects. So for instance, the time of arrival, tau L, is now equal to 2 times the distance over the speed of light. This is because when the signal is emitted, it goes towards the user and goes back, so that's 2 times the distance. When converted to time, we should divide by the speed of light. So we obtain this expression. There is no clock bias as we had in the localization case because the base station is synchronized to itself. The angles of arrival and angle of departure are also a function of the target position. Again, the relation is somewhat complicated, so I don't write it here. Since the transmit and receive array are near each other, there's a deterministic relation between the two. So once, in principle, we know the angle of arrival, we can directly determine the angles of departure. And finally, there's the Doppler. The Doppler depends on the velocity of the object projected onto a unit vector between the base station and the object over the speed of light. Again, since the base station is synchronized with itself, there's no need to introduce any carrier frequency offset, CFO. Finally, the channel gain is modeled through the radar equation. So this is like free space path loss, but then for radar. We have the wavelength, we have the radar cross-section of the object, which determines how shiny it is. We have the antenna gains in the different directions, and then we have here the distance to the power of 4. So these paths are weaker than the paths in the free space path loss equation before. As I mentioned earlier, the targets that are of interest are typically moving against a static background. And we require significantly long integration times to get a good Doppler estimate in order to separate those objects from the static background, which is mainly clutter. Now that we've defined the localization and sensing problems, as well as the associated channel models, let's look at the main performance metrics. The most common metric is accuracy. Accuracy relates to the error that we make in determining the location of an object or a user. So here, in case we do monostatic sensing, the true location is shown in red, the estimated location in orange, and then there's an error between the two. This error is a vector, in this case in the 3D state space. The accuracy is then derived from the statistics of this error. And there's different measures of accuracy. One of them could be, for instance, taking the norm of the error and then computing the percentiles. Another common accuracy metric is the root mean square error. A third common metric is the circular error probability. And these are just 3 of the most common error metrics used to determine the accuracy. Among these accuracy metrics, the root mean square error plays a special role because it can be lower bounded by the Kramer-Rao lower bound. Suppose we have an unknown kappa, which comprises 2 parts, eta and psi. Eta are the parameters of interest, for instance the position, while psi is a vector of nuisance parameters, for instance the channel gain and the clock bias. We have as usual our observations y and k, where n is a sub-carrier index and k is time, which depend on kappa through a nonlinear mapping mu, plus noise. We can then compute something called the Fisher information matrix of kappa. This is a matrix, G of kappa, of dimension equal to the dimension of kappa times the dimension of kappa. And it is given by this expression on the right. The computation of the Fisher information matrix is rather mechanical. It involves taking the derivative of mu with respect to kappa, computing this outer product, taking the real, summing over all the independent observations, and then multiplying by 2 over n naught. The Fisher information matrix is now used to compute the Kramer-Rao bound of the parameters of interest, eta. It turns out that for many estimators, eta hat, the RMSE can be lower bounded by a function of the Fisher information matrix. Namely, we take the inverse of the Fisher information matrix. We then take the components related to the parameter of interest, so here d of eta is the dimension of eta. Then we take the trace, which means we sum across the diagonal elements, and then we take the square root. And this is called the Kramer-Rao bound of eta. The position error bound is a special case of the Kramer-Rao bound, when eta is the location of the user. The Kramer-Rao bound is very useful. On the one hand, it can serve as a lower bound for different estimators. So we can use different estimators and compute their RMSE and compare to the lower bound. Once we have an estimator that is close to the lower bound, we know we don't need to look further for better estimators. It can also be used to design system parameters, such as base station placement and waveforms. This is because the observations, and thus also the functions mu, depend on the transmit signal and the base station placement, so we can optimize them to maximize the Fisher information matrix or minimize the CRB. Finally, and this is one of the most important points of this presentation, is that accuracy, while of course an important metric, is only meaningful when objects can be resolved. When two propagation paths are too close in angle, delay, and Doppler, they blur together, and this leads to resolvability issues, which then severely affect the accuracy. So let's now define resolution. Resolution refers to the ability to resolve multipath components. Suppose we have here a monostatic sensing scenario, and now there are two cars. When the base station is emitting a wideband signal, meaning with a large bandwidth, those two cars will become resolvable in the delay domain. They will be visible as two separate peaks. On the other hand, when the base station is sending a narrow band signal, the two paths will blur together and it looks as there's only one object. So only one car will be detected. To talk about resolvability, it is interesting to know that all the dimensions have a similar form. In particular, suppose that we have some dimension and we observe observations yn across this dimension. And these observations are of the form of a superposition of different paths with complex channel gains alpha L, and then a linear phase progression depending on some parameter omega L plus noise. Now this omega L can be interpreted in different ways. It can be a function of the delay and the subcarrier spacing in case this yn is measured across subcarriers. Omega L can also be related to the sign of the angle of arrival of a linear array in case yn is measured across the array. It can also be interpreted as a product of a Doppler and a time symbol duration when yn is measured across time. So all of these dimensions have a similar form, which helps us to introduce resolution also in a similar way. So as we said, resolution is the ability to resolve paths or objects in different domains. We have delay resolution when the difference in delay is larger than 1 over the bandwidth. We have angle resolution when the difference between the angles is larger than 2 over the number of antennas for a linear array. And we have Doppler resolution when the difference between the Dopplers is greater than 1 over the total coherent integration time. And all of these expressions are derived from this common form. Note that we need only resolution in one domain. So when we have those two cars and we have very limited bandwidth, they will not be resolved in the delay domain, but when we have lots of antennas at the base station, they can be resolved in the angle domain. So resolution is only needed in one domain for two objects to be resolved further on. Let's look at some example. First, let's look at the figure on the right. In this case, this is a range plot where we have 5 objects in an environment starting at around 120 meters and then spaced 20 meters apart. When the bandwidth is 120 megahertz, we see 5 peaks. So we see our 5 resolved objects, and then later we only see noise. When we reduce the bandwidth, but we have the same 5 object presence, this is what we will see as our range plot. So we see a pronounced peak here at 200, and then these side lobes, but we cannot say that there are 5 objects in the environment. The situation is even worse when we further reduce the bandwidth to 6 megahertz. So at most here we could say that there's 1 object in the environment. So this shows the impact of resolution. If we don't have a resolution, there's no even point to talk about accuracy. We can only talk about accuracy after we've resolved the multipath component. We will now look at an example in more detail regarding this first path in the presence of the other 4 paths. So we consider a single antenna bistatic sensing scenario with 1 or 5 objects with an inter-object spacing of 20 meters, and all of the objects give rise to the same channel amplitude. We now then take an OFDM signal and apply a simple FFT-based channel parameter estimator and determine the first peak. So we want to localize the first object, so this object here, by looking at this FFT output after going into frequency domain. We now evaluate the performance of this estimator as a function of the bandwidth. So the x-axis is bandwidth, the y-axis is the RMSE of the first object. We have a number of curves here. So the black horizontal line refers to the interpad distance, 20 meters. The line in orange refers to the resolution. So we see the resolution gets better and better the more bandwidth we have. And after a bandwidth of about a little bit more than 10 megahertz, the resolution is better than the interpad's distance. Then in red, we have the case where there's only one object. The red full line is the Kramer bound when there's only one object. The red dashed line with the circle is the root mean square error of the estimator when there's only one object. And we see in this case that the root mean square error and the Kramer bound coincide, so our estimator is efficient. When we now have the 5 objects and we try to estimate the first object, we have the Kramer bound here in blue, and we have the estimator here in the blue dashed line. So we see that when the bandwidth, the resolution given by the bandwidth is better or lower than the interpad distance, we can attain the bound. So for bandwidths on the order here of 30 megahertz, our estimator gets close to the bound. What happens for lower bandwidth is, first of all, we will misdetect the number of paths, so the metric of accuracy becomes meaningless. Also, the CRB starts to become very, very large. This is because the Fisher information matrix becomes rank deficient. So all in all, this tells us that accuracy is only meaningful after we have resolvability. As a side note, I should mention that the resolution thresholds can be improved when using so-called super resolution methods, such as Esprit or Music, which have no real resolution limit at extremely high SNR. Now let's look at practical localization and sensing methods. Suppose again we have this downlink localization problem where we want to localize the user from downlink transmissions from multiple base stations. If we want to do optimal estimation, we then consider the unknown kappa, which depends on the parameters of interest as well as nuisance parameters, and the observations are this nonlinear function of the unknown parameters plus noise. To estimate kappa, we could do standard maximum likelihood decisions, which means that we take the log likelihood function and then we do a high dimensional search over kappa. However, this is problematic because of the high dimensionality of kappa and also because we don't know the number of paths, so even we don't know the dimension of kappa. In practice, therefore, we usually do a two-stage process. We first estimate the channel parameters, the delays, the angles, the Dopplers, and with those channel parameters, we then perform localization or do target state estimation. So let's first spend some time on channel parameter estimation. One way to do channel parameter estimation is to first estimate the unstructured channel. You can do this by sending enough pilots and using enough combiners at the receiver, and then apply a least squares estimation to get the channel estimate for each subcarrier and each transmission. For a one-dimensional case, this leads to the following special cases. So we would have then an estimate of the channel across the dimension, which would be a superposition of paths, with complex channel gains, and then a linear phase progression depending on the index and a so-called spatial frequency. If the estimate is done across subcarriers, then the spatial frequency, omega L, depends on the delay in the subcarrier spacing. If the estimation is done across the antenna elements, then the spatial frequency depends on the sign of the angle of arrival for a linear array. And finally, if the estimation is done across time, then the spatial frequency would depend on the Doppler shift and the symbol duration. No matter which dimension we look at, we always have the same structure. So we want to estimate the spatial frequency of all of the paths based on the observation h hat. You can already see from this structure that by applying an FFT and looking for peaks, you can in principle recover the spatial frequencies. We now generalize this to multiple dimensions because we don't just have one dimension. For many dimensions, we can take the observations, so the unstructured channel estimate, and restructure them as either a very long vector or in a tensor. If we consider a very long vector, we would have a data structure which is a superposition of paths and then Kronecker products for all the dimensions. We have the delay steering vector as a function of the time of arrival, a Doppler steering vector as a function of the Doppler, a receiver steering vector as a function of angle of arrival and azimuth and elevation, and a transmitter steering vector as a function of the angle of departure and azimuth and elevation. This would be a very long vector with a size that depends on the product of the number of subcarriers, number of antennas, and so forth. We can also restructure the same vector into a very big tensor. So where here we have d-dimensional tensor if we have d dimensions. We again have a superposition of paths, but then we have the product of all of the dimensions with the corresponding indices and spatial frequencies, and then finally the tensor of the noise. Let's look at an example. Suppose we only have two dimensions, namely the subcarriers with a delay steering vector depending on the delay tau L, and angle of arrival with an array steering vector depending on the angle of arrival theta L. And suppose now we observe the signal across the antenna elements and across subcarriers. Then our unstructured channel estimate we could write in a vector notation as a superposition of paths with complex channel gain alpha L, and then the Kronecker product of the two steering vectors plus noise. So the data structure h hat is a vector of length, the number of subcarriers, times the number of antennas. We could also restructure this as a matrix, because now we have two dimensions, the tensor becomes a matrix of size number of antennas by number of subcarriers by removing the Kronecker product and instead writing it as a transpose. So this is maybe a more common form in a matrix structure. If we look at an element in this matrix, so on antenna element I1 and subcarrier I2, we would have this structure here where we now explicitly see the angle of arrival and the delay appearing, with I2 being the subcarrier index and I1 the antenna index plus noise. And now it is very clear that this sine of theta L can be related to the spatial frequency of the first dimension, and tau L can be related to the spatial frequency of the second dimension. By taking a 2D FFT of h hat and by looking for peaks, we can directly read off those spatial frequencies and then convert them to the angles and delays. So this procedure generalizes to more dimensions as shown on the left. And this is now a kind of standard multidimensional harmonic retrieval problem for which there exist many methods. So I've mentioned FFT, but you can also do orthogonal matching pursuit, esprit, and so forth. No matter which method you use, what you get at the end is the estimated number of paths. For each path, you get the paired angles of arrival, angles of departure, delay, and Doppler, and a corresponding covariance matrix, which you can compute by a Fisher information matrix argument. After you've estimated the paths, again, now we focus on localization, we take the paths with the shortest delay as a line of sight path. So we have for those paths the angles of arrival, angle of departure, delay, and Doppler, and the corresponding covariance matrix. Of course, in practice, you do not know that the first path is really line of sight, and to figure this out, you need to do some consistency verification by having either more base stations or some prior knowledge of where the user is. The channel parameter estimates of the line of sight path from the ith base station are a function of the user state plus noise. And this function is nonlinear because it contains delays, the angles, and so forth, which are a nonlinear function of the user state. So as we've seen before, the delay, the time of arrival of the line of sight path with respect to the ith base station is the distance to the ith base station over the speed of light plus the clock bias plus some noise. So now the way that we find S from these observations eta hat I1 is by doing nonlinear optimization. So what we do is we take the sum over all of the base stations, and then we have this kind of weighted least squares cost function, which tries to minimize the error between the reconstructed observation and the measurement weighted by the error variances. Again, this is a difficult problem to solve, but you can often solve it by first having initial guess based on geometry. For instance, you could use all the time of arrivals to compute hyperbola, find the intersection of hyperbola, and then do a local search with respect to this cost function. Once you have the estimate, then you can also compute the Fisher information and then have a way to quantify the error covariance of the user estimate location. And this is then the final estimate of the location plus its covariance, which you could then give to a higher level algorithm, for instance, to do sensor fusion or tracking. This brings us to the conclusions. So we have introduced channel and signal models for localization and sensing. We've talked about two metrics for localization and sensing, accuracy and resolution. And we've also seen that multipath resolution is a main limiting factor for attaining high accuracy. We also discussed some of the standard methods, which first do channel parameter estimation and then followed by localization. This ends the part 1 presentation. If you want to know more about the state of the art and challenges towards 6G, I recommend that you also watch the part 2. Thank you.